Good morning. My name is Dan Ambray. My company is Full Spectrum Diagnostics. I'm here on behalf of Grace Engineered Products. We're going to do a three-part webinar today, Thursday, and next Tuesday, discussing the basics of vibration analysis. A little bit about my company out of Minneapolis, Minnesota. We have a vibration analysis training division. Our training is aligned with guidelines put in place by the American Society of Non-Destructive Testing, or ASNT, and the ISO, International Organization for Standardization. Everything we do in the field goes into our training materials. So most of our instructors spend at least 50% of their time in the field getting hands-on experience and understanding how real systems work. We also have live certification training and interactive training, and that's becoming more popular with all the virus problems. There's webinars going on like crazy now. We're part of that. So if you like what you see, there's plenty on the website that I'll be showing you at the end of the presentation, and you can come find me, and I'd be most appreciative. We also, sorry about that. We also have a machinery analysis division. Our specialty is experimental modal analysis and operating deflection shape analysis. But basically what it boils down to is the animation type format we have on the right here. This is the animation of one of the problems in the machine. This was a refinery pump in Wyoming. And you can look at it and you can say that it doesn't look right. It looks like it's out of phase with the motor and something's goofed up in the coupling. Everybody sees it right away in an animation. I've spent years talking about vibration. I can put a room to sleep immediately. But if I have an animation, I throw it up like this, everybody can see what the problem is. Everybody has a part in the solution. So I have a little corny saying down here at the bottom, but it's true. Our process is making vibration analysis visible and workable throughout the customer's management chain, such that they can be involved in their own asset management solutions. And everybody gets involved when they see an animation. We also have a imaging division. We use Imiscope ODS videos. Basically, it's a high-speed video vibration analysis. We take high-speed clips, we put them through something called an optical flow algorithm, which enhances the displacements, rescales the amplitudes, and it allows us to see what the human eye can't perceive in any video animation, either because it's the event's too fast or the displacements are too small, or both. So here you can see there's some type of problem in the machine. It's moving awkwardly. What it turned out to be, I'll give you a short version of this, is there was a problem in this foot of the motor, or the structure under the foot. This base plate was grouted in, a big C channel or I-beam channel around the outsides. They pumped grout in. It delaminated from the base plate, so it was lifting. So you get this kind of diagonal vibration going in there, and put a little color on it. This should be all gray down here. There shouldn't be any color to it at all that just tells you that there's some motion there. So the only way we found this was with a vibration video, which was very interesting. Okay, this part one, Introduction to Vibration Analysis. We're going to have first a high-level overview of the predictive maintenance process. Now this is going to be recorded, and you can get a copy of the recording. You can watch it as many times as you want. Instead of sitting there and making notes or anything like that, I would suggest you just sit and absorb it, okay? I might have to talk a little fast. If you're writing things down, you're gonna miss some things. So just sit back and have fun. So it's a high-level process we're gonna look at first. We're gonna look at the measurement to analysis cycle all the way through, and that's the core of vibration analysis. We're going to look at the vibration fault periodic table, and that was the first table that was on the screen you saw before. This is structure and method. This allows the vibration analyst to think logically about which faults apply and which don't. And we're going to walk through a series of examples on that. So there's 35 faults on the table, which encompasses most rotating machinery problems. They're logically sorted and grouped with respect to the dominant frequency content and the dominant directional response. And they help us zero in on the root cause problem. Okay. You know, there's always difficult problems that there might be 2 faults or 3 faults dominant, you know, going on at the same time. This will at least get us in the ballpark, but most of the time it takes us right to the root cause. And the final topic, we're going to touch on the industrial Internet of Things and artificial intelligence in vibration analysis. So I've done this for a couple of years, and I look at technology and I see how different companies are progressing. There's companies out there making transducers and having databases, and everything is wireless to the cloud type applications. This kind of looks at that, where we're going and what we've done. And actually some of the things that we've talked about a couple of months ago at Grace Products, they're doing things that are following that path, and it's a good way to go. It's going to be really exciting in the future. This is the very basics of vibration analysis, and in blue at the top there, the best way to start any vibration analysis training is to provide an overall process view of the main concepts. So here it is listed out. I have my picture on the side. There's 7 steps to define the machine of interest. And this is important because we have to know what type of alarms to put on it. Not every machine is the same. And statistically, we're going to be able to pull out an alarm level. This is 0.325 inches per second. So a velocity overall measurement we can put into our database and set up as an alarm, if just knowing the type of machine we have. We're going to measure with a calibrated transducer, so 100 millivolts per G. The analog signal is a voltage versus time waveform, and there's multiple wiggles in that waveform. We'll talk about that. We're going to digitize that signal and sample and digitize and turn it into a format that's not an infinite analog signal so that we can get our hands around it. And then we're going to pump that into an FFT processor, a fast Fourier processor. Fast Fourier is a way of extracting the periodic events in the time waveform. So you have that complicated waveform, and below it there are several more simple waveforms. It's a combination of sinusoids in there, and the processor does that for you. So a fast Fourier transform takes you from the time domain, which is here, into the frequency domain. So now we can see the amplitudes and the frequency content of that complicated signal, and it's 99% of vibration analysis is in the frequency spectrum. So this is how it's done. So a simple equation, frequency is 1 over the period. We can go through it manually, but for complicated problems, complicated waveforms, it's much better to use the processor. This is great knowing what frequencies are there, but we really have to know how much is too much. And this is the Vandalarm version of that. So we can set up our alarms based on what kind of machine we have and have this little stair-step threshold level that we're going to look for as far as good or bad. Okay, and we can trend all that and run our statistics on our alarm bands and our overall levels and get a good idea if the machine is starting to progress towards a failure mode. Here's a little graphic that's kind of nice. If you are listening and you want a copy of this, I can't give you the PowerPoint, but I can give you a PDF of the presentation if you're interested, and email it to you. Let us know. This is where we start. We need to know our machine. So this machine is an overhung direct coupled fan. So on my list of different types of machines, this is an acceptance criteria, this is an alarm value. All these are statistically set. So I would grab a bunch of reciprocating compressors. I would look at all their overall amplitude levels and take the mean plus 3 sigma and get an effective alarm level for that machine, and do that same exact thing with all of these different types of units. So we have some graphics here, cooling towers, 3 different kinds of compressors. There's 5 different kinds of fans or blowers. There's motor generator sets, chillers, turbine generators, horizontal pumps, and vertical pumps. Okay, and we get a a good idea of what our machine is and what their alarm criteria is. So in this case, the little icon is telling me 0.325. So I have a direct driven overhung fan, 0.325 inches per second, which is a velocity level, and it gets us in the right form for setting up our database. This is a transducer, so it comes in a lot of different forms. This is just a single axis transducer. The ones that we're going to talk about a little bit later are typically 3-axis triaxial MEMS accelerometers. We'll talk more about it. But the direction is very important. Where we go with this one, we're going to measure the machine with a calibrated transducer. Typically, it's an accelerometer. It gives us acceleration. Accelerometers are the best transducer to use, but acceleration is not the best unit to use because it has a problem we'll talk about on Thursday with some of the basics of vibration. It changes amplitude with speed or with frequency. So we have a problem with the acceleration parameter and the displacement parameter. Velometers are expensive. They give you velocity directly, but the accelerometer is easiest because they're cheap and you can mathematically integrate the signal and get velocity out of it. Okay, a lot of jargon, a lot of stuff, not real important that you know that right now, but accelerometers and velocity are the preferred method. We're going to acquire data in multiple directions. If we have a triaxial accelerometer, we just put it on top of the housing, we get X, Y, and Z in one shot. If we have single axis transducers, we're going to have to move them and measure horizontal, vertical, and another one in the axial direction that's not shown here. Why is that important? If you look at this cartoon that I've made, as the unbalanced vector swings by my red transducer, it's peaking out. As it swings by my blue transducer, it's peaking out 90 degrees later, or a quarter of a revolution later. So this is telling me a couple of things. It's telling me that what the frequency is going on in the machine. I can see that from my periodic event, and I can calculate that. I can see the amplitude, but I can also see the phase shift. So there's something going on differently in the vertical and horizontal direction. Okay, and it's just due to moving our transducer 90 degrees. But this will tell us if we have a balance problem. If we have a misalignment or a looseness or a cocked bearing or bent shaft, we're going to get a different phase relationship. And that's one of the things we're going to talk about in the industrial Internet of Things, the wave of the future, if you will. Okay, so we're going to, direction is very important. Vibration faults are directional. You got to keep that in your head. I have a little little animation of a bearing. So on a shaft, it looks like the bearing's cocked, and in fact, the inner race of the bearing is cocked. So it's kind of pitching the shaft every revolution. Okay, but what's important here, we're going to capture an analog output from the transducer, and it has all the different wiggles, all the vibration of everything that transducer sees is presented here. Okay, I'm going to tell you what those 3 wiggles are. You can't see them right now, but you will in a minute. One is the rotation of the shaft. It'll put itself, turning speed of the shaft will put a big peak in the spectrum. The other is between each of these balls, there's a carrier that separates the balls and keeps them spaced at the right intervals, so they don't bunch up on one side of the bearing. It spins with the shaft, but only about half of shaft speed, about 40% of shaft speed actually. And the third rotating system is the balls themselves. They're spinning as they roll on the raceway. So you have 3 rotational events going on. The transducer's picking them all up in a raw voltage versus time signal. We apply transducer sensitivity, typically 100 millivolts per G, and now it's a time waveform in acceleration. Okay, because the transducers typically, accelerometer will pick up acceleration. We can mathematically change that like we talked about a moment ago, but we don't have to do that right now. So there's the 3 shaft rotation, the train rotation or the cage of the bearing, and then the rotation of the rolling elements themselves. Number 4, we sample and digitize the data. We can't take in to the FFT processor an analog signal. Analog signals are infinite. So we sample and digitize a very high rate, and we grab points, enough points that it really is a bunch of dots, but they're so close together that it looks like a line. Okay, so we get a good representation of the signal. And then we do where all the magic happens is the FFT processor. The FFT, the fast Fourier transform, basically takes a time domain signal and turns it into a frequency domain signal. The way it does that is it extracts the individual periods and defines them all. So if you look at this first period, it's part of that waveform. I got 3 different rotational events going on. This would be the lower frequency one, the cage frequency, but you can see it. As you look at all the peaks here, you can see a subtle wave in this thing. And it starts here, it waves through, and it ends there. So any periodic event, it'll start at a certain point, it'll go to a maximum, it'll go through 0, go to a negative maximum, and then back to 0. Okay, that tells me how long that event is. If we know how long it is, we can calculate the frequency. The frequency in hertz is 1 divided by the period in seconds. So if we know this is half a second long, 1 divided by 0.5 is 2 hertz, 2 cycles per second. Okay? If we're like RPM or CPM better, cycles per minute, we multiply it by 60. So that's just a unit change. But that's how they're extracted from here. The FFT processor is pretty complicated. This is the simplified version of that. But we'll pull out the amplitude and frequency of period 1, the amplitude and frequency of period 2, and of period 3. So now frequency-wise, we know what those 3 peaks are in the frequency spectrum, as well as their amplitudes. So here we are. We got our 3 periodic events. We extract them all. We apply this Fourier transform, and it gives us those 3 peaks and where they're spaced in the spectrum. So if we have the turning speed of the shaft, frequency 2 here, then this is subsynchronous. It's below running speed, below turning speed. This is 1 times RPM, so it's synchronous. And this, we're going to have to calculate what that is, how it relates back to the turning speed. I'll show you in a second. So what's important? We can identify each peak's frequency, which peak is the rotating speed of the shaft. That's really important. And how do the other peaks relate, or what ratio do they have with respect to the rotating speed? And the last concept is, how do we judge the severity? We don't have any criteria quite yet. That's on the next slide. Now this looks complicated, and it's pretty easy. It's once you have it set up, it's kind of a cookie cutter type thing. So this was setting up alarm bands for bearing health for rolling element bearings. Okay, something that we have. So we have rolling element bearings. We're going to use this parameter. We'll have an overall level, which comes from whatever machine we have. So our overall level is going to be 0.325 inches per second. We'll have subsynchronous, which is 20% of the overall level. That's the amplitude we're going to have. We have a 1 times RPM range, where it'll be 90% of the overall level. We'll have 2 times RPM range, or twice running speed, and it's going to be at 40%, and 3 times is 30%, and blade pass frequency ranges and bearing defect ranges are 20, 25, and 15%. So we set this up with an idea of how machinery fails. If it's 1 times RPM, turning speed of the shaft, or some small harmonics of that, they're going to be a threshold type alarm. When we get out here, the way bearings fail, the alarm amplitude is very small. So we're trying to pick out really tiny peaks, basically, out of the spectrum and apply alarms to them. The nice thing about the database, you can set your alarms any way you want, and you can set them up to learn so that they'll adjust these levels. These are a good starting point, the 20%, 90%, so forth. Statistically, you can look at every band, and you can use as many bands as you like. The result is we have frequency amplitudes, and we can compare some severity criteria to them. So I have this stair-step program, and it looks like my frequency at turning speed of the shaft is exceeding that, and at this higher frequency out there. They also, once you're in a frequency format, you compare everything to the turning speed of the shaft to see what frequency it is. Frequency 1, 739 divided by 1760, the turning speed of the shaft, I get 0.42 times RPM. So it's a subsynchronous frequency. It's below turning speed. If I have a peak at F2, I basically do the same thing, kind of a no-brainer here, but 1760 divided by 1760 is 1 times RPM. It's turning speed of the shaft. So physically it's turning 1760 times per minute, but it is the 1 times rotational speed of the shaft, once per revolution. Okay. 3, this mystery frequency out here, 8,025, I divide it by 1760, and I get a fraction. It's not 4 times, it's not 5 times running speed, it's 4.56. That's telling me it's non-synchronous or it's non-harmonic, and typically that's a varying frequency that might be showing up. Okay, we'll get a little bit more in detail with that as we go. This is how we would commonly take our data, and usually it goes into a database, and the database applies the alarms and tells us what's bad. And right now it would shoot out an alarm report that would say our 1 times RPM peak in position 3 on the shaft, so the fan bearing 3, fan bearing 4, they both exceed the criteria in the vertical direction on those 2 bearings. So that gives us some good information to go and hunt for what the problem is. Okay, so everything's a process of elimination. We start with what is the problem, what can't be the problem, and we move through the whole series, which takes us to the vibration fault periodic table. So this is an invention of full spectrum diagnostics. We use it in all our training. It gives everything structure and a logical sorting mechanism. We have several things that we're going to talk about. One is there's 35 faults on the table that encompasses just about everything in rotating machinery. It's organized by frequency content, which is the columns. So there's a synchronous range, there's harmonic, there's subsynchronous, non-synchronous, and modulation. And we'll show those in detail in a moment. It's organized by directional response, and that's the color of the tile on the table. Red is radial, yellow is axial, and orange could be radial or axial. Usually it's by design. If I have a gearbox, it's the orientation of the teeth which really tells it which way it's going to respond. So if they're in an orange category, they can be either. And lastly, once we've sorted by frequency content and directional response, we can look in the tiles that remain on the table, and they'll tell us what kind of diagnostic to do. And the diagnostics we have are a phase analysis, a time waveform analysis, orbits, transient analysis, or an ultrasonic analysis. We don't need to know what those are. We just need to know what to do next. You know, if you're sitting down with your vibration guy and you're a supervisor, it's very likely you don't know a whole lot about vibration analysis. This is made for the manager, the supply chain, the asset managers, and the whole system to help them understand vibration. And I do this for every analysis I do. I will basically show them this PowerPoint presentation and say, here's how I narrow down your problem. And it's 5 slides, 7 slides, something like that. And we get a logical sort down to here's what your problem probably is. And it's really helpful. You know, they don't know anything about the diagnostics I do, but I just explain them. This is exactly what I've just said to you. It's synchronous problem. It's in the radial direction. It's one of these 4. We do a phase analysis and we weed out which one is the oddball in here, and we're to our solution. Yeah. Pretty much as simple as that. But life throws you curveballs every once in a while, like every week for me. We're going to look at synchronous faults. Okay, so what is synchronous? Synchronous is turning speed of the shaft. Turning speed of the shaft, very important. This is what we want to compare all the other faults in the table to. So if our fault is at turning speed, and our past example was 1760 RPM, that's going to be what we focus on. So if it's at turning speed, synchronous fault, it's one of these 11 things. And we have to throw in our little oddball. Natural frequencies can occur at any frequency. They're predominantly based on the mass and stiffness of the system that's vibrating. Okay, so if they get close to turning speed, you can amplify the response, but they're in every category. So we have to prove or disprove everything on here. So right now, synchronous problems, we got rid of all these other grayed out tiles, right? So we went from 35 problems down to 12. So what do we do next? We look at the color, and then what do we do next? We look at what our little icon tells us to do. Okay, so there's synchronous problems, and synchronous is turning speed of the shaft. So here, in this case, 1784, we divide it by 1784, we get 1 times RPM. Okay. Little fault cursor, I put a little circle on here. The squares are the harmonic cursor. So in your software, you can probably put your cursor on the main peak and see how the other peaks are related to it, right? So 2 times RPM, 3, 4, 5, and 6 times. So this is probably a blade pass frequency, and I have 6 blades on a pump or a fan. And I get a pulsation at that frequency if it's exactly an exact multiple or an exact harmonic. Okay, here's our harmonic faults. Harmonic faults are exact multiples of shaft speed. Okay, notice there's a little overlap. When I have a synchronous problem, it's a dominant 1 times RPM, and usually there's a dominant 1 times RPM in this column as well, but it's at 2 times RPM as well, so that you can have a 2 or 3 times running speed harmonics will start showing up. You still have to figure out phase-wise what the problem is, and they all have a little phase icon in there, but for nothing simple. There's always some overlap. Harmonics are coupling misalignment, bent shaft, another coupling angular misalignment, cocked bearings, and even that animation I just showed you this morning of the bearing and the balls going around, it had a cocked inner race. So it was rotating and producing usually a twice running speed harmonic. So harmonics, these are 1 and 2 times usually. This column is based on the design of the machine. So I'll get a gear mesh at whatever the tooth count times running speed is. So if I have 53 teeth on my gear, I'll get a 53 times running speed peak in the spectrum. If I have blade pass frequency like that last example, 10,704, and I divide it by 1784, I'll get exactly 6 times. So 1, 2, 3, 4, 5, I'll get exactly 6 times running speed. That'll be my harmonic. Okay. This column is looseness type problems, and they'll generate a whole string of harmonics, either fractional harmonics, exact fractions, or 2 times, 3 times, 4 times, 5 times, just a whole string when it starts to get loose. Okay. And here's my example. If I have blade pass frequency and that frequency exceeds my threshold, I'll see how it relates to turning speed. 10,704 divided by 1784, I get 6 times. So it's an exact multiple. It's a harmonic of running speed. Okay. That tells us there's 6 blades on the fan or the pump that we're inspecting. Okay, subsynchronous faults, faults that occur at frequencies less than turning speed of the shaft. So if I have a cage frequency, like we noted before, it was at 0.42 times running speed, it's less than 1 times RPM. Okay? It's one of these types of problems. So looseness problems can show it, rubs, some gear problems, some electrical problems, and oil whirl in journal bearings, and so forth. Subsynchronous and non-synchronous overlap on these 2 columns. So we can have low frequency subsynchronous and non-synchronous problems. Okay. But basically the main definition is subsynchronous is less than turning speed. Here's my example. I have a peak at 749 CPM. I have a peak at 1 times RPM, 1784, and I divide those two, I get 0.419 times running speed, so subsynchronous. Okay, and you can see on the graphic, obviously it's below running speed. Non-synchronous is a group that is not equal to multiples of shaft speed. So they're not harmonics. So anything in between the whole number multiples of turning speed are what non-synchronous frequencies are. And this includes oil whirl and oil whip. All the bearing, rolling element bearing frequencies are all non-synchronous. And so how can that be? There's so many different kinds of bearings. I had a bearing database that had 18,000 bearings in it, and there were 3 that were exact harmonics. But you just take it out enough decimal places and it's going to be non-synchronous sooner or later. Anyway, so we have several different non-synchronous peaks sources. One of those is this problem, and this is a good one because it's so tight. I have a peak that shows up at 5441. I divide it by running speed, 1784. I get 3.049. You always take them out 3 decimal places because this is not a harmonic. It's not 3 times, it's 3.049. So it's really close. There's your 3 times. So I have 1 time, 2 times, 3 times, 4, 5, 6. This is my harmonic cursor. So I am not at 3 times, I'm just above it. Okay. Seems subtle, but you'll get the idea. So that is very likely a bearing defect frequency that's showing up. The last grouping is modulation. This is what shows up, well, a lot of times you can hear it. It's a pulsating combination of faults. So here I had that's pulsating combination of faults. Listening to it, you can hear the pulsing sometimes. Measuring it in the time waveform, a lot of times it's a lobing beat frequency that you'll see. But in the spectrum, it's something a little bit different. It has what's called sidebands. So the only way to show you this is to show you by example. I have my peaks I've been playing with all along. It's still the machine at 1784 RPM turning speed. I have my harmonic cursor. None of these line up. They're all non-synchronous. Okay. I put my cursor on 20,516 divided by running speed. I get 11.5 times running speed. So it's non-synchronous. It's not 11 times. It's not 12 times. It's 11.5 times. Okay. So I start doing the same thing with all the other peaks. Divide them by turning speed. So I have 13.5, 12.5, 11.5, 10.5, and 9.5, which is they're all non-synchronous, but they're all separated by turning speed frequency. So 20,516 minus 1784, I get 18,732. And I subtract turning speed from it again, I get 16.9. So this is how modulation works. There's a center frequency that might be some known frequency, and then sidebands on either side, plus or minus the exact spacing. So we'll get more into that as we go, but that's one of the fault categories, the last one. Okay, so we sort it by frequency, and then we sort it by color or direction. In this case, the dominant direction for the red blocks is in the radial direction, so either horizontal or vertical or both. Okay. The dominant direction for the yellow blocks is axial. And this is the big separator in the synchronous problems. So we can eliminate, if we have radial response, there's 4 possible synchronous problems that produce radial response. If we have an axial response, there's 6 possible. Okay, and the gear is orange, it can be in either direction. but we can wipe out a whole bunch of possibilities right off the bat with knowing what direction is dominant. Oh, and there's one oddball out here, the bearing cage frequency, the spacer between all the balls. When it rotates, if there's a thrust load on it, it will respond in that direction, and you'll start to see an axial peak in the spectrum, which is unusual. That's the only one that bearing frequencies acts in the axial direction. Radial and/or axial fault group. This is a lot of times by designing the machine. So if we have a gearbox, it can be a right angle gearbox, it can be herringbone, it can be a spur gear. That configuration might give us an idea of what direction is going to be dominant. But as far as we know, it's a gearbox without looking inside. So it's orange. It can be either direction. Electrical, they can be multiple directions, natural frequencies, turbulence, things like that. There's no really pronounced direction. It could be any of the three. And then we narrow down the possibilities. So the recommended diagnostic is the icon in the upper right-hand corner of each tile. And I mentioned before, we have phase analysis, time waveform, orbit, transient, and ultrasonic analysis. Okay, phase analysis, very good for synchronous problems. Time waveform, very good for gear type problems. Orbits, if I have journal bearings, that's what the best method we use to figure out what's wrong with them is with an orbit plot. Transient analysis for different natural frequency problems, and ultrasonics for bearing problems. So bearing inner race, ball spin, outer race, and cage frequency, and even bearing natural frequencies will show up occasionally. Okay, so they all have their place. This is telling us what to do. So I've sorted by frequency content, I've sorted by direction, and then I go and do my diagnostic test to narrow it down, hopefully to the root cause. All right, so this is a lot of stuff, but without a demonstration, it's not as acceptable. So we got one more little twist on this. So I got a real world example here. We have a AC induction motor, it's direct coupled. We have a bearing, it's a center hung fan, inner and outer bearings, they're rolling elements in this case. So everything's set up. What else do I have? It's an AC motor, so it's not DC. Okay. I'm going to start the sorting process based on this. So the first thing we can do, we don't have any vibration at all. Here's a series of blocks that are design related. So we have to consider that machine design, the drive type, the coupling, the driven machine type, the bearing type, and the rotor configuration. And we're going to walk through each one of those for our example here. So I have an AC induction motor. I can get rid of DC electric problems and fluting, as long as this, and you might not know what fluting is. It's electrical erosion of the raceways in the bearing from discharges of either current or voltage. So if this was a DC motor, that occurs sometimes. AC induction motors on variable frequency drives, it can also occur. So, but if it's just an AC induction motor, usually it's electrically, it's pretty good, and you'll never get the erosion problems. But there's two blocks that we, just based on what we know about the machine, we can get rid of those two. Direct coupled, meaning that there's no gearbox. So the 4 gearbox problems go away, and 2 belt drive problems go away. Okay. Rolling element bearings throughout. My oil whirl and oil whip, these are journal bearing problems, they go away. Center hung rotor, my overhung rotor unbalance doesn't apply. It's not a specialty machine, so there's something called roll barring in the paper and aluminum and steel industry that doesn't apply to this. And what happened? All of my gray blocks here, I went from 35 possible faults down to 23, and I haven't done any vibration analysis yet. It's all based on machine design. Okay, and I can't tell you how helpful this is. A lot of times you'll try to prove that you're running through it in your head as you're doing diagnostics, and you forget about certain things. You say, what about this problem or that problem? and it's already off the chart. If you don't have this chart, this structure, logical sorting mechanism, you go in circles sometimes, and I've been there. Okay, we're going to consider the frequency grouping. So this is the data for our machine, our direct drive, direct coupled overhung fan, or center hung fan. We have peaks in the spectrum. There's nothing axially. There's nothing in the horizontal direction. Vertical direction, the motor's fine. And bearings 3 and 4, there's a vertical 1 times RPM peak that's showing up in the spectrum. Okay, how do I know this is 1 times RPM? That's how this alarm band is generated. So I have a little 1 times, I have a little 2 times, and I have a little 3, 4, 5, 6 times. Okay. So that's how we originally set it up in the database. So the database is telling us you have alarms at position 3 and 4 in the vertical directions at turning speed of the shaft. So it's a synchronous problem. It's at turning speed of the shaft. It's at 1 times RPM. It's the first 2 columns on the table plus the natural frequency. So we had all these blocks selected. Everything that's not synchronous will also go away. So those blocks all through here, except for natural frequency. So it's not a bearing frequency. It's not electrical. It's not all that. It's synchronous. So we're down to 9 problems. We went from 35 to 23. Now we are at 9 potential problems. We're going to sort by color next, or by direction, dominant direction. And you go back to this, there's no axial vibration, which is nice. So horizontal and vertical, they're radial vibration, and only the vertical one has the alarms to it. So we can say that this is not an axial problem. So the yellow blocks go away. And we're stuck with, after just sorting 2 times and removing the faults that are based on design, we're down to 5 different faults that it could possibly be. Okay, so what do we do next? We do what the table tells us to do next. We perform a recommended diagnostic. Upper right-hand corner, we have phase, 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 and phase for these synchronous problems. And we have transient analysis for the natural frequency problem. Okay. This is one of the 2 tests that we traditionally use to look for natural frequencies. One is a waterfall plot, where we can start or stop our unit, or if we have control of speed somehow, we can either do a startup or coast down, or a controlled speed change, and we can see if there's a peak in the spectrum close to some operating condition. Okay, the easier way, I think, is to do a natural frequency impact test. So you get an instrumented hammer, you hit the machine like ring it like a bell, and the frequencies that come out of that ringing are telling you what the natural frequencies are. Okay? So we do that type of testing all the time. So in this case, we couldn't find a natural frequency. So what's left? These 4 phase diagnostics for unbalance, eccentricity, looseness type A, and alignment offset in the radial direction. What are those tests? These are the categories. So doing the phase test, not really important right now. Understanding it, what it gets you is very important. So I check for unbalance and eccentricity. I should have a horizontal to vertical phase shift of 90 degrees at each bearing. So all I do is check the boxes for those that apply. I do a little survey of the whole machine, see how one point is related to a reference location, and I can see how it's moving, just a rough animation of the machine. I check for misalignment across the coupling. If the coupling's moving out of phase, either radially or axially, it's a good check for, hey, you got something misaligned in that coupling. In this case, we didn't have that. We had normal unbalanced conditions at low level. We had no eccentricity. The only one we did have, we had a lot of vertical response, and that's a good signature for soft foot conditions. So basically it had a foot that was shimmed improperly, or had too many shims, or they forgot to do it, or the bolt was loose or broken. There's some condition in one foot on the machine that gave us fits. And in this case, looseness type A is that type of fault. So we end up with looseness type A. Okay. Everybody can understand this. It's just sorting things and using what you know to eliminate problems. And if you can't eliminate them, they stay on the table. Okay, I'm going to jump to a little different topic. The industrial Internet of Things, artificial intelligence, and vibration analysis. I have about 15 minutes left, I think. I'm going to try to get some questions in after this. If you guys have questions, you can type them in to your computer and they'll show up on the facilitator screen, and we'll answer those. So this is something I've done the last couple of years, and I continue to look at where the technology is going with a wireless transducer, in-cloud data storage, all that type of stuff. The gold standard is the thing that everybody's looking for is the permanent wireless transducers, 24/7 monitoring that can do a lot of things. And the four things that are of main interest right now are overall vibration trending, which is just an energy level response of the machine, and overall ultrasonic trending, which is a filtered high frequency failure mode for rolling element bearings. You'll get really small impacts that you can only see in the high frequency range. A lot of people are going to that, having transducers that can do both. On-demand time waveform and spectrum capability. It's real important if you have an overall level that exceeds a certain criteria that you do a waveform or a spectrum to see what's really going on in there. There's some clue frequency content wise what's happening. And then probably the hardest one is on-demand phase analysis, or in my case, animation capability. I'm showing you a pump, and it probably had 30 measurements on it. And these were all amplitude and phase type measurements. They were all simultaneously acquired. So I can see how the machine's moving, and I can get an animation like this. If we have on-demand phase analysis, meaning can one transducer link and talk to the other one simultaneously, then we can do something like this on a rudimentary scale for every machine. Assuming things in the future keep going the way they are, and these wireless transducers get smaller and more battery efficient, and you can link them all together on a machine. You can put just a sonar net of transducers on your machine and get all kinds of animation response and phase response. Gold standard is also the transducers are powered by an infinite energy source, which never will happen, but battery technologies get better and better. So that's something to watch. Transducer sensor nets that can talk point to point and acquire data simultaneously. We just kind of went over that as far as that's what this allows. And actually we can do phase analysis right away. That can be part of the algorithm. If we have a point to point acquired data, we know the phase shifts from point to point and what they should be. We can program that into our software, and we can basically have smart machines, smart sensors. Artificial intelligence algorithms designed for trending, detecting, assessing, and defining machinery problems. This is phase analysis that we can do on the fly, which would be fantastic. Vibration data trending interfacing with other plant process variables. Most MEMS transducer will get you temperature as well, which is good. They can do pressure, or well, they can't, the transducer can't, but the plant usually will have pressures, flows, speed, and efficiency on some type of data system or PI system. The idea is to link to that so we can get another, non-vibration measurement that might be part of the puzzle. Infinite data storage and monitoring capability in the cloud, everybody's going to that. So it's not inexpensive, but it seems like we have enough data storage now. And the real thing is to work on the price and the battery life. So the price point is low for these MEMS transducers, and they are triaxial most of the time. and it's a good place. There's going to be a big jump soon, I think. This last one is on-site vibration analyst is eliminated or replaced with remote online monitoring. I think we're not there yet. That might be in the future. There might be just smart algorithms that will tell you when your machine's going to fail, but vibration is so subtle sometimes, and so there's multiple things that happen, and it defies the linear logic sometimes. But the more transducers you have, if I had 24 transducers on my machine instead of 4, I could do a lot more. So it all depends on, you know, pricing of transducers and how they can link together and acquire data. This is kind of the flow chart. So I have acquiring data with my transducer up here. I can also acquire phase data, like we've mentioned. If all these transducer locations are linked together, I can get live phase analysis, which is fantastic. So we have overall vibration levels, we have time waveforms, we have spectrums that we can capture, right? Right now, we're doing little packets of overall levels. So we're getting the least diagnostic information. But if something changes and goes into alarm, that prompts us to take a spectrum, take a waveform. And we don't have to take it everywhere. We can target the location that the alarm came from. So once we have that, we can start using this type of logical sorting mechanism that will be able to tell us what the root cause of the problem is. Current state of the art is route trending. And why do we stop that? There's a lot of inaccessible locations. There's dangerous things that you can't monitor as well as you'd like to. That is perfect for permanently mounted battery-powered units. Especially a lot of places I go, like refineries. There's, you know, you just don't want to be close to some of these machines. What they have out in the market right now, battery-powered units, they do everything. They do the trending, the ultrasonic, the spectrum, the waveform, phase analysis, orbits. They can do all kinds of natural frequency tests. Anything you can think of, they're throwing into these portable units now. It's just, you know, you have to have a skilled guy that knows vibration and knows how to use it and to get the most out of it. Databases were constructed with these, so we're uploading and downloading data constantly. They don't really have algorithms. They have some statistical analysis they can use, but you do have to have a vibe guy that knows what he's doing. Infinite storage, storage really isn't an issue anymore with hard drives being as big as they are. Price point is low and acceptable, and when you throw all the costs in, I came up roughly at about $25 a point, which is what, $400 a machine, no, $300, sorry. So not bad. On-site or contract vibration required, yeah, there's still a place for that. Manual route-based portable data. So this is the kind of stuff you're going to get. You'll get a spectrum. You'll get overall levels. So here I'm moving between different overall levels and going in and out of alarms. And you can see how the spectrum's changing. This is what we don't get, this spectrum over here, from just a single point. So this is just telling me I'm at, don't have that number, oh, Y. Here I'm at 0.334 inches per second. So I'm in alarm, but this is the information I need to make a call on a piece of machinery. Okay, there are supplemental spot checking methods. A lot of places will give the operators, like in power plants, an overall meter, and they'll go out. It's battery powered. It's storing just a value. There's no algorithms, minimal vibration analysis training required. Data storage is limited, but you can download it. Price is low, so it's good. You're making use of your operators, the people who are walking around writing something on a clipboard. Instead, you're getting an actual measure. But it's only as good as the operators make it. This current wireless system options, a lot of them, the first one, they're going to semi-permanent mounted data collection to get some of this capability. Transducer battery powered in some cases, and sometimes they're wired in as well. But here's the thing that makes it really valuable. If you do a route-based vibration analysis, you're only getting about 12 measurements a year at any given point on your machine. 12 measurements is tiny. I have an example here to the right. This was 4 days worth of data, one data point per hour, so about 94 measurements. If we get this, we can get better uniform data collection because it's magnet mounted. Nobody's walking around and touching a different point. It never gets moved. You're going to get better repeatable trends, and you're going to get massive amounts of data. If I'm route-based, it's 12 measurements a year. If I'm wireless rate on a permanently mounted transducer, if I do 1 per day, I'm getting 365 measurements in a year. 1 per hour, almost 8,800 measurements. I get about 500,000 measurements if I do one every minute. So we know this is crazy, but how crazy is it? When I look at this, I'll get to that in a minute. Okay, price point is lower, still need a vibe guide, so forth. Okay, this data is the starting point. So I have some alarm levels that are mean plus 3 sigma. It's based on the real data, and it's just statistics. Okay, this is where the alarm probably will occur. This was a plot of regular vibration velocity, which are the red dots, and this scale is acceleration. So it's peak view, it's ultrasonic measurement, and some of the stats on that. But this is what you can do with the single point wireless transducer. You can take that data and you can get, this was 94 measurements. This was 1 an hour, and I can see massive statistical changes. The gray was initial, the first couple hours, it's pretty ragged, and then all of a sudden it starts zeroing in on a much better statistical alarm level. And this is only 4 days. I think it's something that's phenomenal for just a basic vibration monitoring. You still need to get a spectrum and a waveform, but it's telling us a lot more than we think it is. And I was just using basic statistics and having them update every hour, and it gets a really nice trend. Evolving systems, wireless semi-permanent mounting data collection. There's a lot of them out there that will do wired and battery powered, or you have the option of either. Data stored. Spectrum and waveform can be collected on alarm or by request. That's really important because you don't want to be pumping spectrum every day. You'll get you'll wear the batteries out in no time. Price point still high, capability is increasing. So it's out there. It's elusive. Every time we want to do something, it's, hey, what if we do this? And that might cost a little more money. So it's pushing in the right direction, but it's got to be evolving all the time, which I believe it is. This is one of the time waveforms from one vendor out there, which is horrible. It doesn't even look like a vibration spectrum or a time waveform spectrum. This is the spectrum, which looks pretty good. And I don't think these were collected at the same time. This looks like noise to me. This looks like harmonics. So there's maybe a looseness problem or a misalignment problem. It's telling us something is going on here, and it gives us a clue. This is another vendor where they narrow banded everything. This is a rolling element bearing raceway frequency, and it was on a gearbox, and it was just buried in the noise floor. So we have to put it on a log scale, put some specialty alarms in it, and we could start picking it out. So there is a lot of things you can do with the databases as far as pulling things out that are very subtle. Okay, future battery-powered transducers, unlimited life is what we want. Power compromise, We'd love to go just full battery. Our transducers are getting better. The MEMS design, the micro electromechanical systems, so MEMS. Integrating plant process parameters, creating algorithms, and we haven't even started creating algorithms yet for real subtleties of overall vibration. Synchronization of transducers to get phase analysis. Basically the elimination for on-site vibration analysis, which I don't really approve of. I think he has a very useful function, but you know, if you supplement it with an off-site guy or a contractor, you can also do that. So here's our grand overall look at everything. We acquire our data, overall trends, time, waveform, spectrum. We're isolating potential problems. We're pulling up our current rule base and seeing what's good and bad, overall vibration or individual peaks in the spectrum. We're comparing that to plant processes. So where are we on the pump curve or the fan curve? That could be the entire problem, but we're never comparing our vibration to plant process, and maybe we don't know that. We update our machinery animation, so we can have, depending on what kind of net of transducers we have, we can get some decent animation, and then even applying a rule base for potential faults. So maybe this is moving like this, but it's not high enough amplitude that it's an issue yet. We can still say, hey, here's our potential problems. We might have a loose foot or a soft foot. We might have misaligned coupling, and we might have some blade pass frequency problems that are showing up. And then we apply that and get a better idea of where we sit statistically, and then start the process over. So it's doing this not 12 times a year, every hour, every minute, you're getting an update and a better idea of what your machine's trying to tell you, if it's hurting or if it's fat, dumb, and happy. All right, I've blown through an hour, barely. Sorry about that. I tried to hold it to an hour. If you guys have questions, I think Nick will get back on. If you need to contact me, or you want a PDF of this presentation, I'd be more than happy to email you one. So let me know. And you can contact me if you have any other questions about training. You there, Nick?
Hi, Dan. Yeah, we got quite a bit of questions here. I'm not sure if we'll be able to get through all of them, but I'll go ahead and start at the top, and we'll see how many of these we can get through. I'll also save these questions, everybody. We will do our best to address some of these in the next few webinars, or like Dan said, you can reach out, forward your questions to him. The first question is from Brian. Is all of this based on everything being new, or is there a way to put this on machines already installed and running in the field? And how do you know where your base would be on that used equipment?
Yeah, no, you can put them on anything. You know, if it's a starting point when you put it on a machine, right at the beginning, we define the machine as a direct drive, center hung fan, whatever. And we can say, hey, here's statistically where our starting point is 0.325 inches per second is our overall alarm level, right? If it's a brand new machine, then you're seeing it as it's starting to wear. It should be, you know, running beautifully. If it's a used machine, it's down the road years, what have you, you get a baseline. But again, you're taking measurements. Your first day or two of measurements could be every 5 minutes or every 20 minutes or what have you, and you could get a couple thousand measurements and really understand where the actual overall alarm is. So instead of 0.325, it might be at 0.298, something like that. And that doesn't sound like a big deal, but it is. You are resetting your statistical alarms with real data in the machine. And it doesn't lock you into every fan of this configuration has the same alarms. They're all different. So each one, you'll get a value. Statistically, it's close to that 0.325, but you're going to have enough data in a day or two to define a better statistical overall level that you're interested in as an alarm.
Great. All right, next question. How can you detect the modulation if the base frequency is different from the shaft RPM?
The modulation of the base frequency.
Different from the shaft RPM.
Well, if there is a modulation, there's two different frequencies involved. One is usually a center frequency. The example I used would be more like a bearing defect. So that center frequency was non-synchronous, and all the other ones were non-synchronous as well, but they were spaced at a turning speed. So that gives me a clue, and not that you might know this, but that gives me a clue that it's a bearing defect and what kind of bearing defect it is. When you're going in and out of the load zone of the bearing, on an inner race defect, it'll modulate 1 times RPM. So every time it goes into that load zone at the bottom of the bearing, and it's once per evolution, you're getting that modulation effect. And the more the modulation, that means there's more wear or there's more defects or spalling, what have you. But there's a lot of different modulations that you can look at. Rotor bar pass frequency in a motor is a subtle rotor problem, but it'll depend on how many rotor bars there are. So the center frequency in that grouping in the spectrum would be 38 rotor bars. I have 38 times running speed. Its sidebands would be spaced at the electrical frequency, 2 times line frequency. So 60 hertz, it'd be at twice that. So I'd get 7,200 CPM sidebands. So they're not spaced at 1 times anymore. They're spaced at 72. So that'll give you a clue what's going on. I don't know if I totally answered your question, but there's some subtleties to it.
All right, next question is from John Davis. For electrical faults, how much do VFD operating frequencies skew or affect the data? In other words, does the VFD frequency variation significantly dirty the data?
It can. A lot of times, like if you're in a wireless transducer, you're going to be taking data all the time. So the VFD is likely moving with the process and changing your shaft speed. The real problems that come into play are being consistent with your data collection. Now you're moving your shaft speed all over the place and it's changing the overall response, but eventually you'll get a handle on that. The other, and you can compare it to plant, you can probably go in the plant pi system and try to see where you're changing speed. But the other thing is, if you're changing speed and you have a natural frequency close or in that range, you can amplify the natural frequency and have other problems. Those are the big drawbacks. It's usually if you're in a route based, you'll set the VFD to a value 60 or 40 or 50, whatever you normally run at, and you'll lock it in and you'll take your data at that frequency. Now you have consistent data, throughout the year, but you might be missing something due to that speed change. That's the real limiting factor.
All right. Next one, what is the difference in vibration reading using a portable on top of the bearing housing versus the probes?
Versus the proximity probes, I assume you're saying. If you have a transducer on top of the housing, you're measuring the housing vibration. If you have proximity probes, they're designed to be installed through the bearing and within 50 mils maybe of the shaft. So they put out a magnetic flux that can vary with the distance in that gap. So it tells you how the shaft is actually moving. It's light years more sensitive than a housing measurement on an oil film bearing. So you're looking with the probes, you're looking right on the shaft, you know that there's 6 mils of vibration, 6/1000ths of an inch, something like that. Whereas if you're on the housing, you might not detect anything across that barrier. Okay. It's just the animal it is.
All right. For the example you used, would the AMCA standard be used to set the alarms with the bearing clearance?
AMCA, bearing clearance. Are we, I assume we're talking journal bearings again. And send me an email if I'm wrong, but usually you set your gaps basically for journal bearings with proximity probes at whatever the manufacturer says is half the internal clearance of the bearing. So once you get above half the internal clearance and you're vibrating that much, let's say you have 7 mils of internal clearance and you get 4 mils of vibration, you're above that 50% level and you have a better chance of having instability. So you can set off an oil whirl or an oil whip type problem, or just increased wear and looseness. I don't know if that's the exact answer to the question you had, but.
Yeah, like I said, everyone, you guys can follow up with Dan in an email, get your specific answers. Let's see. So this person, Eric Weber, says we use 50 horsepower motors belt driven to a fan blower to move paper scrap to the collection point. How would we be able to tell the difference between machine failure and the scrap moving through the blower?
I guess statistically, you'd have some noise floor. So the scrap going through is going to be random. So you're going to have an energy level. You'll see the peaks, you'll still see the blade pass and the rotating speed and things like that. It'll just be a noisier spectrum. If you can average it, I didn't think about that. I guess you can average it over time, but if you're randomly throwing scrap in there, it's just going to affect the noise floor. So as long as your peaks are above that, you'll still be able to pick out the peaks. I'm not sure if you can tell real well if it's good or bad as far as the condition of the fan that's pushing the stuff through.
Okay. What are the possibilities to not only diagnose existing problems, but forecast the failure based on trends?
That's how we do it now. Everything's a trend. You're looking at how things progress. And this last part of the presentation on having a transducer that's in place at all times and it's taking data at a much higher rate than just the route-based guys, you're going to get a really good trend. It could be a little problem getting bearing defects to show up because they're pretty subtle, but for any other threshold type thing, the synchronous vibration, the harmonics, blade passing, things like that, electrical frequencies, you'll see a good trend developing for those. The bearings are a little harder. That's why you need a separate measurement of ultrasonic energy. So I think Grace actually is they have a triaxial set out there, but they're putting in one of those triaxials as a much higher frequency range. And if you filter that signal, you can see minute impacts of the bearing frequencies as they start to fail. So I think your question has already been thought of, and people are putting an answer in place right now.
All right. We are an electrical engineering services and solutions company doing power system studies, harmonics measurements and analysis, etc. We want to add mechanical field service as well as condition monitoring. How should we start?
Well, you can find a guy that knows anything about vibration. You might not be the best guy, but anybody to start with. You might have somebody come in and evaluate them. I've gone into places and given them a real simple test on basic ideas and fundamentals, and see how they do. But you get a guy that's kind of qualified, that's into it, that wants to do it, and you put him through a training program. So there's entry level classes. There's AS&T and ISO have 4 levels that you walk through, and you can take 1 or 2 levels and you'd be fully functioning. You know what you're doing. But training's always good. It's find somebody to train, like maybe Full Spectrum Diagnostics might be able to help you with that. But get some training and see which guys do it the best, and those are your guys.
Awesome. All right, well, I'm going to end it since we have a lot of questions. We'll do our best to follow up on these afterwards. But I'm going to end it right here on this comment from Eric Foreman. This is the most concise, effective vibration presentation I've ever seen. Thank you for your time this morning. I'm really looking forward to the next 2 sessions. We're looking forward to you guys all attending the next 2 sessions with Dan. Again, that's Thursday, April 9th, and next Tuesday, April 14th at 10 a.m. to 11 a.m. Central Standard Time. Dan, do you have any closing remarks?
No, I appreciate the comments. I hope everybody felt that way.
Me too.
I do like constructive criticism, though. If I'm being goofy or not saying the right things, I'd love to hear it, so I don't do that again. So let me know.
All right, and everybody, this is our first custom webinar series with different dates. I know a lot of people had issues getting the calendar dates added. We're going to be sending out an email after this webinar with those calendar dates for the next 2 sessions. It was primarily Outlook users, I believe, that had the issue. So we'll be following up with you on that. We're going to send out a PDF of the presentation. And then once this series is complete, we're going to edit all these together and make an on-demand video for all of our registrants as well, who either had to leave early or missed it or weren't able to attend for some reason. So with that, we will close it down here. Thank you all so much for attending, and we look forward to seeing you on Thursday. Thank you, Dan.
Yeah, thanks. Do you want me to hang on the line?
I'm going to go ahead and end the webinar now for everyone. Thanks again, everybody.